Hello and welcome to this YouTube channel, guys. I'm Abhishek Pandya and you are watching lab 6 of analog circuits. In this particular lab, we are going to focus on the biasing configurations of BJT and how to make gates, the logic gates using BJT. Okay, so inverter, NOR, NAND, these gates, how do we make them using BJT and how do we verify the VTC or voltage transfer curve of inverter. Basically, we are going to learn about all these things. So without wasting any time, let's get started. So starting with the lab 6 BJT biasing circuitry. There are two parts in this lab, part 1 and part 2, going through all of them by one. So objectives is to determine the quiescent operating conditions of the fixed and voltage divider bias BJT configurations. This is also like a hardware lab. There are two transistors, 2N3904 and 2N4401, and you need to calculate these different values and different things, currents and voltages in these two transistors. This is the lab, and we have to start with the part A. So part 1, in that part A, fixed bias configuration. So I hope you already know about this fixed bias voltage divider bias configurations and how do you calculate the different values from them mathematically or analytically. Okay, so this is the configuration you can see here, and this is the BJT. VE is 0 because it is grounded, VB will be there, VC will be here. So measure all. So basically you need to start with all the steps one by one, and then finally you have to compare this 2N3904 and 2N4401, the different values from them, the difference of beta, IC currents and all these things you need to measure, and you need to calculate both analytically and also with the help of LTspice. Okay, so measure all register values from circuit in figure 5.1 using DMM, record them. The DMM is digital multimeter. Of course, we are not present in the lab right now, so basically you are not going to measure anything, but eventually we will put this to these values RP, RC and VCC in the LTspice. Okay, so you are not going to measure this. Such. Second is construct circuit as shown figure 5.1 using 2N3904. So do that. So basically this thing you need to perform in LTspice. Second step, measure the voltage VBE and VRC, record them. Okay, this you can do by using basically by using .op command. Calculate the resulting base current IC and using the values obtained and find beta. So these things you can also calculate with using the LTspice, right? So beta is a factor which is already mentioned in the model file. Okay, I am going to show you that. But IC is equals to beta IB, and if you have IC and IB values, you can calculate beta from that. So that is that thing. By using the values obtained in step 4, calculate the VB, VC, VE and VC. See, there are two things. One, you have the value of beta and you will calculate all the things by analytical method. And the second thing is that you will directly go in LTspice and you will check that what are the different values of VB, VC, VCE and all. How do the measured values compare to calculated values? So basically that is you are calculating analytically, and that you're getting through LTspice. Comparing them is this 7th step. Then same steps which you have performed for 2N3904 for 1 to 6, replace the transistor 2N3904 with 2N4401 and do the same things. Okay? From the values obtained, determine beta value for 2N4401, same thing, right? So compile all the data and table 5.1. So there is a table 5.1 here. This is table. So basically this is the resultant calculation part. So here you have to write all the things, right? Whatever you have calculated, equations are also given. So all the things you can calculate from here. Okay, and you need to fill all these things you have to write this and calculated and measured. Measured in the sense here it is obtained from LTspice, and calculator means you have calculated by analytical method. And comparing the steps and the VB 9th step and 10th step, where you compare this VC value, IC value, IB value and the beta. Okay? This is table 5.1. Last in the 11th step is finding the difference in beta or percentage beta change that happens because of changing the transistors. Okay? So this is all the things you have to perform, and this is the part A. Okay, so let's just go through LTspice first. So this is the circuit, right? This is known as fixed bias configuration, right? So going to LTspice, so this is the circuit. Same 1 mega ohm, 2.7 kilo ohm resistor, VB, VC, VE. Okay, and this 20 volts is given as a VCC at the input. Okay, so basically this is the 20 volts, and all the DC values you can calculate. Just press this. Basically this is the op command, and IB, IC, IE, VC, VB, and VE. Basically this is VE, but it is grounded, so VE is 0. All the values that you want to measure, or actually in the lab when you will measure this value, you will be getting this values in different DMM. Okay, but here you are getting these values, so compare these values. IB is what? 19.29 micro amperes. IC is 0.0059 amperes, and so basically IC by IB you will be able to calculate beta. Okay, so all the things you need to perform and calculate from here. Okay? VC and VB are also given. So this is the values that you are getting, or the measured values, and the calculated values will be there with the help of the beta which is present in the system. Okay, so let me just show you that as well. Right clicking here and going to model files. This is 2N3904, and the beta values here is 300. Okay, so this is 300 value, beta value. With the help of that you can calculate different values. Okay, analytically you can also calculate, right, because this transistor will have a definite VBE drop, so eventually you will be able to calculate it. So basically this is 0 voltage. The VB voltage of this 2N3904 or the cutoff voltage you can calculate. You will have the fixed value here, so that value will be given here. Okay, so 0 plus the cutoff voltage value of this 2N3904 will be the VB value, and it will be constant. Okay, now because you have this voltage available and this voltage available, you will be able to calculate IB, and you have beta, so you will be able to calculate IC. So 20 minus IC into 2.7 will be the voltage available at VC. So you will have VE, VB, VC, IB, and IC, right? All the values you can calculate like this. I am not going to calculate them, but I have explained you the method by which you can calculate this. Okay, so calculate and compare. And the second thing is there. So right click on this, pick new transistor, and this is 2N3904 from NXP. We also have 2N4401, which is from Fairchild, the manufacturer. So basically there is this thing, and here the beta values are also given, so you can calculate different values from here. Okay, same thing which you have performed from 2N3904, do it for 2N4401, and this beta you can just calculate in different values. So this is the first part, or part A of the lab 6. Okay, that is about the fixed bias configuration. Now let's go to the voltage divider bias configuration. So this is the part B for lab 6 in part 1. So voltage divider bias configuration. So first thing, measure all resistor values R1, R2, RE and RC. You are not going to measure them, you are directly going to put them here. Okay, and using the, and basically first step is to record them in DMM. So in the hardware layer you will do that using the beta determined for 2N3904 transistor in part A. Calculate the theoretical values of BB, VE, IE, and all these things, all the DC parameters. Record them in table 5.3. Construct the network of figure 5.2 and measure this thing. Okay, same things which you have performed in part A, but here doing that for voltage divider bias. Measure the voltages VR1 and VR2. Calculates IE, IC currents I1 and I2 using Kirchhoff's current law. How do the calculator and measure values 5.3 compare? Okay. So do that thing. Then compile the measured values of BCE, IC and IB. simply remove 2N3904, replace that this value, the 2N4401, and do the exact same process. Calculate the magnitude of the percentage change in the each quantity due to change in the registers. Okay, that's the same thing. And place the results of the calculation in table 5.5. Okay. Using the piecewise simulation, find the values of this thing, and yeah, okay, this is the instructions. So going to the tables and the part B here. Basically, this is part B. So you have to fill in this all things: R1, R2, RE, RC, VB, all this DC parameters. Okay. Then same thing will basically calculated and measured, or calculated and obtained from LTspice. Both the things, all the parameters you just compare here, and working for I and IC you can show. I1 and I2 comparison of calculated measured values 5.3. So table 5.3 is this, right? So from there you can obtain this. Then sixth is like changing the transistor and seeing that value change, and the values all are given, right? So equations are already given, you just have to put the values in them. Okay, and yeah, then changing the percentage beta, percentage IC, delta, VC, and so on. This is the lab 6 part 1 part B. So just going here, second part. Okay, so this is the voltage divider bias configuration. Okay, and this is 2N3904 transistor, and all the DC parameters you can obtain by .op command. Okay, so just go here and press this DC op point, and yeah, operating points. Yeah. So IB, IC, VC, VE, VB, all the things are given. Okay, so VE will have, these are the values of voltages available. Okay, IC and IB are given. IE will be this value, and yeah, so this is the all the DC parameters. Okay, current from this I1, R1, voltages you can calculate just like this, right? So R1 value is there 22 kilo ohms, and the current through R1 is 0.007 amperes. Okay, so multiply these two values, you will be getting the drop across it. Okay, so that's it. The calculation of the measured or the obtained values. So how do you calculate the values actually, right? So I think you already know about it. So this is the voltage divider bias, right? So this is ground and this is 20 volts. So there you will be able to calculate VB, right? VB is equals to 20 into 6.8 kilo ohm upon 22 plus 6.8 kilo ohms. You will have VB. So VB minus the voltage drop of this transistor here will be VE. So you will have VB and VE. You will have VE so that you will be able to calculate IE. Okay. So VE upon 680 will be the IE. Okay, you will have basically when you have IE value, you can calculate all the IB and IC values, right? Because IE is equals to beta plus 1 IB, this and IC is equals to beta IB, right? So you will be able to calculate all the values on the basically available in this design. So basically all the currents, that is IB, IE, IC, VB, VE, and VC, right? Because you will have the value of IC. So 20 minus IC into R3 will be VC. Okay. That is the voltage available at collector. So all the DC values you will be able to calculate, right? So this is how you calculate all the values. Okay. So calculating the values and measuring the values and comparing them, and then changing the transistor from 2N3904 to 2N4401. So that is it about the part 1. Okay. So now let's go to the second part, or part 2 of lab 6. So this is lab 6 part 2, Bjt inverter. Bjt in particular configuration behaves as an inverter, that is that input voltage low will result in output voltage high, and input voltage high will result in output voltage low. That is what inverter means. Okay. So exercise A to C in this LTspice, and D in is hardware implementation. So A to C we are going to perform. Okay. So implement a Bjt inverter circuit explained in section 5.10 of the text. Plot the VTC, and in the diagram shown this. Input varying from 0 to 5. In addition, for a steady input, fill up the following table. Okay. see you need to have VE, VB and VC and modes of operation. Okay? So you can either go through .op command, that is giving the value of input voltage 0, VE, VB and VC for all the values here, and modes of operation you already done this before, that VB junction and VCB junction. You basically see these two junctions and you will say that whether it is in saturation or cutoff or linear region. Okay? So that is the thing. Or you can write apply DC sweep, right, for 0 to 5 volts at the input voltages, and you can check all the values of V, VB and VCR. Okay, both the things you can do, and calculate the change of RB and RC while keeping one value constant. Okay? Observe the VTC change in VTC. Okay? This is VTC, means voltage transfer characteristic, okay, or voltage transfer curve. So voltages, input and output, input voltages are transferred to output voltages, of course. So that is what VTC means, and further extended to NOR gate as explained in 5.171. So I don't have the book right now, but I am going to explain you this in a general concept. Okay, I don't know exactly what the circuit will look like, but I have the configuration ready with me. Okay, explain the and then extending into NOR gate, right? So you can make NOR gate also with the help of BJT, or several BJTs. So you can implement NOR gate, NAND gate, and you can find a truth table for that. Okay, implement the above exercise in hardware using this. Hardware part is not required right now. So extending that inverter with NOR and NAND, that is something which you can do and which you have to do here. So now directly going to the lab, okay, in LTspice. So part 2. So this is the general configuration of an inverter. Okay. So this is the transistor which is used. Basically I can use 2N3904. Okay, this is the RB, this is the RC, then this is the ground, this is the grounded, this VE terminal is grounded. Input the VCC voltage is given as 5 volts and VBB voltages are varied from 0 to 5 in steps of 0.1 volts. Okay. So basically what we are going to do is that we are going to see VTC characteristic. Okay, so just press on this V out. So this is that first thing, this is our second thing. So this is how it looks like. Okay, see this very carefully. This is VN002. Basically this is the input voltage or DC sweep from 0 to 5 in increments of 0.1 volt steps, and this is the V out. Okay? So what you can see here is very simple. This region from 0 to 0.5. Okay, so just click here, see the voltages here present. So this is the V out or the output voltage. When the input voltage is up to 0.5 volts or 0.6 up to 0.6 volts, the output voltage remains approximately 5 volts. So there is no current flowing in the system, or IC is approximately 0, and that is why the output voltage is the same as VCC. Okay? So this is known as cutoff region, right? So there are regions like cutoff, then linear, then saturation. All these regions are there. So you can see that when it is crossing that 0.6 volt or the VB junction is forward bias, then the voltage is drastically decreasing, right? So from 5, basically it is decreasing to about 3.4, 3.9. Basically this is decreasing in this very steep fashion, right? Very fast decrement in the output voltage is there, right? You can also add one more trace here, IC. Okay, that will also be seen, right? So this thing, okay. See this very carefully. IC increment, right? See at this voltage after 0.5 volt and 0.6 volt, the increment in the IC is very steep, right? The increment in IC will result in decrement in VCC, the VC voltage, right? Because VC is equals to VCC minus ICRC. VCC minus ICRC is the V out or VC. So this steep increment in IC current will result in steep decrement in V out voltage. So that is the thing. Okay, you can check the operation regions. Okay, you can check that what at different points or point, let's say in the basically that stable there are 0, 0.5, 0. Like 1, 1.5, 2.5, all these voltages. You can just go here and for input voltage 1.5, let's say this, okay, you can basically have this values, right? So input voltage is like 0, 0.5 here, 1 here, and for each of these you can calculate the value of output voltages, right? So you can just directly go here, yeah, and let's say 0.5 voltages at input, you will have 4.98 volts at the output. 1 volt we have, for 1 volt we have 119 millivolts and so on, right? One for 1.5 is 79, then it is 66 and so on, right? So this is how you calculate different values, okay? VB, VC and VE. VE is already 0, right? That is not a very important thing, okay? So yeah, this is how you see the input inverter characteristics, okay? This is what known as VTC or voltage transfer characteristic, okay, or voltage transfer curve. So this is how you can see the inverter characteristics. Now you can extend this to NOR or NAND gate, okay? So let's just see NAND and NOR. I will just explain the NAND one and you can do NOR by yourself, okay? So let's go. So this is the NAND configuration, or NAND type of configuration, where this 2N3904 BJTs are connected here like this, okay? So you need to find just a truth table here. So basically we will give two voltages, 0 and 5, okay, or the 4 possible combinations, 0, 0, 0, 5, 5, 0 and 5, 5, okay? So and we will check that what will be the output at this V out, okay? So let's give 0 voltage here, 0 here, 0 here, and just run this. What is V out? V out is 5 volts, okay? So for both 0 we are getting high, for both 0 we are getting 1. Now let's just change one of them to 5 voltage here, running this once again. V out is 5, okay? V out is not changing. Let's change this to 5 and this to 0, okay? Run this once again. V out still remains 5, and now let's just change both of them to 5. So now what is the output? Let's check out. So V out voltage is now 0 for both 1 or logic 1 or both 5 voltages. The output is 0. Otherwise for all the other cases 0, 0, 0, 1 and 1, 0, it is remaining high, okay? So that is a verification of the truth table of the NAND gate. For the NOR gate, what we will do, you will basically connect this in not like this fashion. You will connect one and basically you will be shorting the collector voltages and you will be getting that at output, okay? So you can do the same thing for the NOR one and you can find the truth table from there, okay? So that is how you will do the this NAND and NOR implementation from the BJTs. So that was the lab 6 with all the calculations and measured values and the LTspice implementations. And so that was it. So that was the video, guys. If you like this video, then like, share and subscribe to my YouTube channel. Comment down below your thoughts, ideas, and I will meet you in the next one. Happy learning.
Tell me pretty lies, look me in the face, tell me that you love me, even if it's fake.